Alright, we want to show that if the potential energy is an even function of x, show that if v of x equals v of minus x, then it suffices to consider even and odd functions of these. Is that called phi? I think it's phi. So that is phi of x equals phi of minus x, or phi of minus x equals minus 5 minus x. So that's the even function, that's the odd function. Okay, and when we say suffice, we mean that any solution can be written as a linear combination of even and or odd solutions. First thing we'll do is we want to assume that phi of x is a solution to the time-independent Schrodinger equation. As we were saying, if v of x is v of minus x, then it suffices to consider even and odd functions. We want to show that if that equaled that, then it suffices to consider even and odd functions of phi, which is the probability of the location of x. And so phi of x equals 5 minus x, which is even, and the other one is 5 minus x equals minus 5 minus x, which is odd. An even function would be a function that rotates like a mirror image, like y equals x squared. The function of that location gives the same y value. Negative x squared would equal y, and x squared would equal y. It would be the same y. And then an odd function would be like a cubic, where you have, it's like rotated around, and this one's reflected. Any solution can be written as a linear combination of even and or odd solutions. And that means that these are the bases. They make up every possible answer. These two directions, east and west, two possibilities, even functions or odd functions. You could say this is the line of all even functions, this is the line of all odd functions. And the answer is a combination of those two. Just like north-south line and east-west line can give you everything on that circle. Assume that phi of x is a solution to the time-independent Schrodinger equation. We assume this first, which is here's the total energy, that's the location, and that's the actual equation of the time-independent Schrodinger equation. We've got minus h bar, this is the reduced Planck constant, it's called h bar. Here is the second derivative, plus v of x, which is the potential, and here is 5x, which is the probability location. Replace x with minus x to see if that's actually true, and look what happens if we put minus x in there. That stays as it is. Minus x squared becomes x squared, and v of minus x, well, that's the same as v of x, because we said at the beginning that that was the assumption. But what happens to the equation? Given that that equals that, as I just said, v of x equals v of minus x, and minus x squared equals x squared, the equation turns into this. Total energy, phi of minus x, reduced Planck constant, h squared over 2m, and still a derivative here, but look, x squared instead of minus x squared, and v of x instead of v of minus x. So what we can see, if phi of x is a solution to the problem, then so is that of minus x. They're both solutions to that problem. In other words, the probability of the location of x can be in the positive or the negative direction. So there are two answers to that equation. We know E is total energy and v of x is the potential, is also a solution with the same Vx and E. That's all that this is. We're just showing that for the Schrodinger equation, we can have two possibilities for the same potential and same total energy.